Okay, I'm back. It's been a while. I live in Louisiana and we had a hurricane. So I'm finally back to my office so I can record some videos. And I'm going to make for you a video that goes over everything that you need to know about building this Python model of the Earth Moon system. So we can see what it looks like. And this is for something else, but it's going to be fun. And I'm really excited. So let's get to the very basics first. So I have here the Earth and the Moon, and I kind of drew it to scale. I tried to draw it to scale, but it's a little bit off. The key thing is that all these textbooks always draw the Earth Moon system poorly, and this is even poor too, because they're so far apart you can barely see it compared to their size. So they usually draw the planet, the Earth and the Moon bigger so it looks better, but we're going to make it realistic, and then we can change it later. So that's where we are. I have all the values here for the things that we need to know, like the mass of the Earth, the mass of the Moon, the radius of the Earth, the radius of the Moon, the Earth-Moon distance, this distance right here. And from that, there's a couple of physics things. I'm going to go over all the physics stuff, and we're going to build the model from scratch. But the first thing is this gravitational force. So if I have two objects with mass, there's a gravitational force pulling them together. This gravitational force depends on the two masses of the objects, mass of the Earth, mass of the Moon. It depends on the gravitational constant g, which I have down here, 6.67 times 10 to the negative 11th. And it depends on the distance between them squared. Now, so this is a vector. I'm going to have to find this as a vector, right? The vector distance between them. And so to do that, I'm going to realize that the Earth can move. And I'm ignoring the interactions with the sun. This is just the Earth-Moon system. So with that, I'm going to say that the Earth is not at the origin. So I can't just use the position of the Moon as the radius. So I need to calculate the vector distance from the Earth to the Moon. And so I can do that with the position of the Moon. I'm calling that r Moon, and minus the position of the Earth. And that's going to be my vector value r. I need to find the magnitude of that and square it. But then I need to also find the unit vector. And we're going to do this in Python, so it's not a big deal. But I'm going to need to find the unit vector for r. And without that, you don't get a vector force. So that's important. So I do need that vector force. Okay. So from that, let me turn off this camera because you can't really see. Well, I'll just move it up here. And then the other thing that we're going to need is the idea of the momentum principle. So the momentum principle says that if I know the force on an object, that's going to be the rate of change of momentum. So if I take a small time interval, in this case, small, it takes 28 days for the Earth to orbit anyway, so small is a relative term. Then I can assume that the force is constant during that time interval and use that to calculate the change in momentum, where momentum is mass times velocity. Okay, so there's actually a little bit more we need to do to set this up, and then we'll jump into Python. And then what I'm going to do is to start off and just let those two things start with an initial velocity of 0 and just kind of move toward each other, and then we'll get into circular orbits. Okay, but here is the key to this problem, because it's really not, if you allow for the Earth to move, it's possible to solve it analytically on paper, but it's very difficult. But using a computer, it's not so bad. So here, let's look at the momentum principle. F net, the vector, is the change in momentum with respect to time. And if I assume that the force is constant during this time interval, which it is not, right? If the Moon and the Earth move anyway, then this force is going to change because r will change. So the force is not going to be constant. And that's what makes this kind of difficult. But if I assume it's constant by taking a short time interval, then I can say this. I can say the change in momentum is going to be P2 minus P1 over delta t. So that says that the momentum at the end of the time interval is P2 and at the beginning is P1. If I solve this for P2, I get P2 equals P1 plus F net delta t. So I just multiply both sides by delta t, add P1 to both sides, and I get this. This is called the momentum update formula. I'm writing fast. Momentum update. Because what it does is, during that short time interval, at the end of that time interval, I know the new momentum. Okay. Now, I can also find the new position of both objects. I can do this for both the moon and for the Earth. And for both objects, I can also find the new position. So let's say the definition of average velocity, V average, is the change in position with respect to time. And this would be both for the moon and for the Earth. So I'm using the same R here, but I'm just doing generically. And if I assume that the velocity is constant, which is not, but if I do, then I can say this is equal to R2 minus R1 over delta t. And I can again solve for R2, and I get R2 equals R1 plus V average delta t. Now, let's say that I use the momentum. I can say P equals mv. So I can use that to find the velocity. And instead of the average velocity, I'm going to use the final velocity. So I'm going to take the momentum at the end of that time interval and use that as my average velocity during the whole time interval, which is totally wrong, but just kind of wrong. If I have a small time interval, it's not so bad. So I'm going to write this as R2 equals R1 plus P2 over M delta t. And this is position update. So now I can update the momentum, update the position, and then do it for another time interval. Now at the beginning of that time interval, what I need to do is recalculate the force, right? Because if the object, both of the objects have moved, then the gravitational forces will be different. So I have to do that. Now, I only have to calculate that gravitational force once, because if I calculate the force that the Earth exerts on the moon, the force that the moon exerts on the Earth is the exact same thing, except in the opposite direction, because forces come in pairs. So this is what I'm going to do. I'm going to do all this in Python. So I'm going to switch over there to Python on my computer, and we're going to do this. And I'm going to start with the Earth and the moon. I'll put the Earth at the origin for now, and then we'll see what happens. I'll put the moon right there. Now, the one thing I do need to pick is a time interval. I'm going to pick, let's see, what did I pick? 1/10 of an hour for my time interval, right? Because if this takes a 28 days to orbit in 1/10 of an hour, I mean, it barely moves. So it's a good approximation for with the force being constant, the momentum being constant, stuff like that. But let's just do that and see what happens. So let's jump over here to Python. Wow, I haven't done this in a while. I feel like I'm out of practice. But okay, so I have Python here, and I'm going to give you this code. Don't worry about that. And I have all my values for G, the masses, and all that stuff. And I will go ahead and make the Earth. So let's make the Earth. So I'm going to say Earth. And one of the nice things about Python is that I have the ability to make these three-dimensional objects. So let's say the Earth is a sphere, and I need in that. Oh, let me make this a little bit bigger. My daughter's texting me for some reason. She's calling. Let's see. Let's just answer that later. Okay, I don't want to interrupt my video, right? Okay, so the Earth is a sphere. I need to give it a position, and that's going to be equal to the vector 0, 0, 0. I'm going to put it at the origin. It needs a radius, and that's going to be equal to RE. Let's just run that and see what happens. And see, there you go. I have the Earth as a sphere. Oops, I don't want to move that one. I want to move this one. Let's put it up here. Okay. The Earth is a sphere, and everything's great. Now, I can actually make that look like the Earth with a little trick. Let's say texture equals textures dot, is it Earth or Earth? Texture equals textures dot Earth. I think that's it. Yeah, there you go. Check that out. So and I can rotate this around. This is a three-dimensional object. I mean, it's shiny and there's a couple light sources and stuff like that, but that's kind of cool, right? I can put it like that. I'm going to put the moon on the x-axis, so it's going to put it to that side. Now, if I do that, technically the Earth's in the wrong orientation, but I'm just going to leave it because I don't really care about it right now. But you could rotate the Earth so that you're looking at it from the top. You know, the moon orbits in a mostly, I'm going to make it orbit flat and circular, even though it's not. Okay, so we got the Earth. Let's make the moon. Okay, so I'm going to put the moon is equal to a sphere. Its position is going to be equal to the Earth's position plus the vector REM 0, 0. So it's going to be the location of the Earth, and I'm going to shift it that way. And then the radius is equal to, what did I call that? I called RE, RM. Why did I do R lowercase m? And let's leave that as the texture, no texture, even though we could give it a texture, and I'll leave it as the default whitish gray. And there we go. So this does not look great, right? Because there's the Earth right there. There's the moon, but that is to scale. That is actually what it looks like. And I think that's kind of cool to see what that looks like. Now, I want to actually shift everything over a little bit. So I'm just gonna shift it over to the, well, no, let's leave it. I don't really care. Okay. If you want to make this bigger, and I'm gonna make it bigger for now, I'm gonna multiply both of these by 10. So now it's not realistic, but it's easier to see. There you go. That's a little too big. Let's do 5. There you go. Okay. Now, one other thing, I want to make the moon leave a trail. I'm not going to make the Earth leave a trail for right now, but let's say make trail equals true. Okay. So now in that option, as it moves along, it's going to leave a trail. Okay. So I have that. Now let's do the following. I have G. I just want to use the momentum principle and find out where it's going to go. So I first need to do this. T equals 0 and dt equals, I told you, I need all my values in seconds. So an hour would be 3,600 seconds. A tenth of an hour would be 360. And let's just see what it does. And now let's run this for 1 month. Okay, so I guess I need to calculate 1 month. So let's say a month is going to be equal to how many? 24 hours per day times the number of seconds per hour times the number of days, which is 28, something like that. Okay, so that's 1 month. And that's how long I'll run it. So now I'm going to say, I'm going to make a loop while, let's move this whole thing up because I don't need that. While t is less than a month, do the following. Now in Glowscript VPython, one thing I need to do is to say how fast I want this whole thing to run. Okay, because if I don't put anything, it's going to do it as fast as it can possibly do it, and I won't be able to see anything. If I do it in real time, it's going to take 28 days to run all the way around. So let's just say this, rate equals 1,000. So it's going to do no more than 1,000 calculations every second. And that's a way to kind of like determine the animation speed. Now the next thing I'm going to do is to calculate the vector r. So r is equal to the, I'm going to have a vector from the Earth to the moon. So this is going to be moon.pos minus earth.pos. Ooh, that's capital. So that is, I used the vector r in my calculation, but moon.pos is the location of the moon. Earth.pos is the location of the Earth. So that is the same thing as r sub e. Okay. And it is a vector because those are all vectors. Now I can calculate f. So f is going to be equal to, I'm just going to write it out, negative g times me times mm times the unit vector r. And in Python, there is a built-in unit vector, and we just call it norm. So if I put norm r, that will return the unit vector for r. And then I can divide by the magnitude of r, and I can square that. And there, that's my gravitational force on the moon. So the gravitational force on the Earth is the opposite of that. Okay, so now I can go and do my fun stuff. I'm going to update the momentum of the moon and the Earth, which I don't have, so I can't do that. So let's go up here and say Earth.p equals vector 0, 0, 0. It's going to start with the 0 momentum, and moon.p is equal to vector 0, 0, 0 also. Okay, now I can update their momentums. So down here, I'm going to update the momentum of the moon. Moon.p equals moon.p plus F times dt. Remember, I calculated the gravitational force on the moon, so that is F. Now, you may notice, well, where is the subscript? This is not an equal sign. This is a make equal to sign right there. This says take the momentum of the moon, add F times dt, and then make that the new momentum of the moon. So I don't need to worry about P1, P2, P3, and all that. It just keeps updating the momentum of the moon. Now let's do the same thing for the Earth. Earth.p equals Earth.p minus F times dt, because the gravitational force on the Earth is the opposite of that one. Now I can update the position of the moon. Moon.pos equals moon.pos plus moon.p, because I already calculated the momentum of the moon. So by putting this afterwards, it's the final momentum. Okay, times dt divided by, what did I call that? mm. And do the same thing for the Earth. So I'll put it right here. Earth.pos equals Earth.pos plus Earth.p times dt divided by me. I don't know why I made that capital. Now, the one other thing I need to do is update time. T equals t plus dt. So I'm increasing the time interval, otherwise this will run forever. And I think this should work. Let's just see. Let's save it. Should I move this? Nah, don't worry about it. I'll just run it. Okay, so that appears to work, right? And this is in real, it's really fast. The Earth and the moon are both pulling on each other, moving towards each other. As they get really close, the forces get really high, and they eventually just pass through each other, and there's a rounding error because I take a small time step and it gets ejected. If you had a realistic time interval or skip that part where they actually cross when R goes to 0 and you get an infinite force, it should just oscillate back and forth like that. But that's not really what I want. I want it to do a circular orbit. So how do we get it to do a circular orbit? Let's go back and look at what initial conditions we would need to make that happen. Okay, so here I have, I'm going to assume that only the moon moves, which is wrong. Okay, but if I do that, I have here the Earth, here's the moon, and I want to do a circular orbit. So the question is, how fast does the moon have to move in that direction to move in a circular orbit? So this is the vector r, or the radius. This is, put that as r. And I know that this is the gravitational force, F. I guess that is technically a vector. If it's moving in a circular orbit, then I can write the following. I can say F, the magnitude of the force, is going to be equal to mass times acceleration of the moon. But the acceleration of the moon is moving in a circle, so this is going to be mv squared over r. That's the acceleration of an object moving in a circle. So, and then I can put that together with my gravitational force. I get g, mass of the Earth, mass of the moon. These are just scalar equations because it's in the same direction. Divided by the radius squared equals the mass of the moon times the velocity of the moon squared over the radius. The mass cancels, or the mass of the moon cancels. One of these radiuses cancels, and I can take the square root, and I get v equals the square root of g times the mass of the Earth over r. So if I know those values, I can put this in for my velocity of the moon and find the momentum of the moon, and then it should be moving in a circular orbit. So I'm going to have that moving in the positive y direction, and let's see what happens. Okay, so let's go and add that in here. Okay, so I need to go up here. Let's calculate V. Let's call that Vm just for fun. And it's going to be the square root of g times the mass of the Earth, me, divided by the distance between them, which is rem, which is a scalar value. So over here, I can put this as 0 Vm 0, and I need to multiply that by the mass of the moon, which I called mm. So now it has an initial velocity going that way. And let's run this and see what happens. Check that out. I mean, you're pretty much done here. But I want to show you something because something does happen. You'll notice that, let's run that for a little bit longer and a little bit faster. So let's run this for 2 months. 2 times that. Oh, let's not change the month. Let's change this 2 times. And let's run it at twice the speed because we don't have to wait. And let's run it again. I wanted you to see what happens here. Notice the Earth is moving. And notice that everything's moving, right? Okay, so I mean, that's okay, right? If the total momentum of the system is not 0, because I gave the moon a momentum in the y direction, so the whole system has to move in the y direction. I can fix that very easily by just cutting this, moving it down here, and then saying the momentum of the Earth is negative the momentum of the moon. And that will give it, because the Earth's mass is so much greater, that's fine. It's all going to work out fine. But now the whole thing's going to stay stationary. Now you can see the wobble of the Earth, and I'm going to plot that for you, just to show you that. And this is not a perfect system, because I did not give it the correct velocity, because I did not take into account that the Earth also moves in a circular motion, so that the center of mass for this whole system is like right in here, right there, okay? And I calculated the velocity based on this being the center, so it doesn't really quite work. I will include a link down below with a video explaining how to determine the correct parameters for 2 objects, especially if they're not the same mass. I'll show you how this is not going to work, because if I make the mass of the moon twice as much, let's say 3 times as much, then you'll notice that it's not going to be working correctly. It's not a circular orbit. Maybe. No, it is a circular orbit. It's just not, completely correct. Well, even then, it's still barely moving. So, but I have a binary star system calculator that I'll include down below. I don't want to get into that right now. What I want to do is to show you that the Earth does move. So let's make a graph of the x position of the moon. So up here, I'm just going to say G1 equals graph, x title equals time. Let's do time. I guess I could do x in meters versus y. I'll do a trajectory plot. And then I'll make a graph. Fe equals G curve. Color equals color dot blue. I will include a graphing tutorial down below also. So then down here, I'm going to make a graph. So I'm just going to say fe dot plot earth dot pos dot x versus earth dot pos dot y. Let's see what that does. Run it. Ooh, an error. Y title punctuation error. Okay, let's see. I did not put a comma. Okay, so here's my plot of, now it's not circular because it is circular, but it doesn't look that way just because the way the graph is drawn, this scale of axis is not the same as that, but it does indeed move. You can see the Earth moves, the moon moves, but there you go. There's your Earth-Moon orbit system. And I'm going to include stuff down below, so hopefully that you find that useful. You can edit this code and rerun it and it's going to be great. And I hope you like that, and I'll talk to you guys later.